Hello, my name is Andre Algazi. I'm with the State of California Department of Toxic Substances Control, and today I want to give you an overview of the regulation of toxic substances under federal and California law. So I'm going to talk briefly about the Superfund Law, CERCLA, the Resource Conservation and Recovery Act, and the Toxic Substances Control Act, as well as California's hazardous waste control law. Before we dive into the regulatory part of the presentation, I wanted to take a step back and talk a little bit about chemicals. For those of you who've taken a chemistry class in the past, this is the periodic table of the elements. All of the substances in our world are composed of combinations of these elements into molecules. Molecules are unique combinations of atoms from the periodic table. Depending on how the atoms are arranged, the molecule will have different properties. It might be useful for a certain purpose depending on how they're arranged. Things like plastics and polymers are long chains of hydrocarbons, for example. Everything that we use in our modern industrial society is composed of molecules that were designed for a particular purpose. So while molecules can have beneficial properties, they can also have harmful properties. They can be corrosive, so they can dissolve solid objects or surfaces. They can be toxic, meaning they're harmful to living organisms. They may be flammable, they may be explosive. There's a whole bunch of properties that can be dangerous. So let's delve a little deeper into toxicity. This man in this picture is a 16th century alchemist named Paracelsus, and his sort of claim to fame nowadays is that he is considered the father of the science of toxicology, which is the science of poisons. And Paracelsus's most famous quote is on this slide, "What is there that is not a poison? All things are poison, and nothing is without poison. Solely the dose determines that a thing is not a poison." So the short version of Paracelsus's most famous quote is, "The dose makes the poison." So toxicity isn't necessarily always a bad thing. Sometimes we actually design molecules because of their toxicity. That could be in certain drugs, maybe chemotherapy agents or pesticides that help protect our food production, preservatives that prevent spoilage of manufactured items or foods, antimicrobials that prevent disease or transmission of COVID-19 virus, things like that. Where problems can arise is when something that is toxic, reactive, corrosive, ignitable, or has some other harmful, dangerous, potentially harmful property is when that material is no longer wanted. Either it's been used and used up and is no longer useful for what it was intended, maybe a solvent, for example. It might be a byproduct. When you're producing something valuable, you might also produce an unwanted material that has a hazardous property of some kind. It just may be inherently some kind of waste. It might be a product that didn't meet specifications and can't be sold or used. So the big distinction between a product or a material and a waste is that the waste is something that really people don't want, that has no. And unwanted materials of this type, in a sort of general sense, are what we mean when we say hazardous waste. A material with exactly the same composition and properties that is wanted is not a hazardous waste. So if you go to a big box store, the shelves are full of products that have labels about the harmful properties that they may have, and those materials and products are regulated completely differently from a spent or unwanted or used container of solvent, let's say. And the rationale for that is that people are more likely to carefully handle a product that has value that they've purchased maybe for some purpose than some unwanted, spent, or off-spec or surplus material. So when people are careless with hazardous materials, big messes can result, injury, death. That is why the regulatory systems that I'm going to tell you about are so stringent relative to what the rules are for handling products. So I wanted to sort of highlight a few examples of bad management of hazardous waste that have led to pretty big problems. This picture is of the Love Canal subdivision in Niagara Falls, New York. And somebody decided it was a good idea to build housing on top of an old chemical dump. A company called Hooker Chemical between the early 1940s and early 1950s buried 21,000 tons of toxic waste at this site. Then it was covered up, houses were built, and later the residents of those houses started noticing odors, chemicals seeping from the ground. This was 10, 20 years after Hooker Chemical had done the disposal. In the end, 950 families had to be evacuated, and cleaning up the site took 21 years and cost $400 million. One illustration of why we have the hazardous waste regulatory system that I'm going to tell you about. Another example closer to home is the Stringfellow acid pits here in California, in Southern California. 35 million gallons of toxic chemicals were disposed of in an old quarry between the mid-1950s and early 1970s. And the quarry was where rock had been mined in the past. And so there were these unlined ponds that the chemicals were disposed of in, and the chemicals ultimately leached into the groundwater and contaminated it. And ultimately, spills and releases of chemicals from this improper disposal of chemicals ended up contaminating a local creek called Pyrite Creek. And even now, decades later, there's still groundwater treatment going on to try to remediate the contamination. State engineers estimate that it will take 400 years to fully clean up the contamination from this improper disposal. And there's a link in the presentation if you look at the notes where you can read an article about that. The next example I'd like to talk about is the Hudson River in New York State. And the Hudson River was badly contaminated with PCBs that were dumped by General Electric from their capacitor manufacturing plants. PCBs are used as a dielectric in capacitors and transformers used for electrical applications. Over a 30-year period, General Electric dumped around 1.3 million gallons of PCBs into the river, contaminating 200-mile stretch of the Hudson River. There was a long-term dredging project to pull up the contaminated sediments that wrapped up in 2015, and more recently, the New York State congressional delegation wanted to do some more dredging because there was still quite a lot of PCBs left behind in the sediments downstream from General Electric's plant. Next, I'd like to talk about a more recent example of messes caused by improper management of hazardous materials and hazardous waste, and that is the Exide battery recycling facility in Vernon, California, in the Los Angeles area. In 2013, Exide was found to have contaminated two yards of houses nearby the facility in Vernon, and they were ordered by the regulators, both my department, Toxic Substances Control, and the Air Quality Management District, to reduce the amount of lead being emitted from their stacks. So this facility would take the battery cores, if you ever changed your own battery, and return it to AutoZone or Kragen for the deposit. It goes to a facility like this one and is melted down to make new batteries. In the process of doing the melting, you generate lead vapors and fumes, which, if you don't have proper air pollution control equipment, can escape out of the stack and contaminate the surrounding area. As it cools, it's deposited. And so that's what happened in the area around the Exide facility. So in 2015, Exide declared bankruptcy. They were reorganized and continued to operate. The plant itself was closed, but they had other facilities. They were denied a permit renewal, and so in order to close down when more extensive contamination was discovered. Later, it was determined that between 5,000 and 10,000 residential properties may have been contaminated by the Exide facility. They were fined $26 million, which was to go into a trust fund in 2016. And subsequently, the state legislature passed and the governor signed legislation authorizing almost $180 million for soil testing from the 10,000 properties and cleaning up about a quarter of those properties. Really recently, Exide has filed for bankruptcy again. This time, I think they're liquidating. They're no longer financially viable. So this slide is to show you the magnitude of the problem, the contamination that was caused by improper management of lead batteries at this plant in Vernon, California. On the top graph, 10,158 properties were within the preliminary investigation area. We had permission, my department, Toxic Substances Control, to collect samples at just under 9,000 of those properties. And as of the time this slide was put together, we had taken samples at 8,555. So around 85% of the properties have been sampled already. The bottom graph shows you something called the California Human Health Screening Level, or CHISL, for lead, which is set at 80 milligrams per kilogram, or 80 parts per million. What the CHISL is a concentration of a chemical, in this case lead, in soil or soil gas. And concentrations below this are considered to be below risk levels of concern for human health. And the basis for that is that toxicologists calculate that there's less than a 1 in a million risk of cancer if you're exposed below the CHISL. So you can see here that of those 8,555 samples, 109 were below the CHISL, and all the rest of the samples that were analyzed so far had lead that were quite significantly above that level of no concern. I should point out that the CHISLs are advisory numbers. They have no regulatory effect, not intended to be used by regulatory agencies, but they do give a sense for the magnitude of the problem in the neighborhoods around this facility. This screen is a screenshot of an interactive GIS map. GIS stands for Geographic Information System. Essentially, it's a way of showing the sampling data on a map, so you can kind of see where the contamination was originally, where it is now. So if you're interested in exploring this right now or after you listen to the lecture, you can click the link on the heading here that says Interactive GIS Map, and you can scroll around and look at the property. The colors indicate whether the property's already been cleaned up, or it's on the priority list for cleanup, or if it didn't need cleanup at all. So there's color coding that indicates the status of the cleanup. And you'll see on this map the location of the facility, and which is the red kind of L-shaped area with cross-hatching in it. That's the Exide facility. So you can see how extensive and widespread the contamination from that facility was. Mostly the lead coming out of the smokestack because of improperly operated or inadequate air pollution control equipment. To address the problem of contaminated sites that became contaminated due to mismanagement or improper management of hazardous waste or hazardous materials, about 40 years ago, U.S. Congress adopted CERCLA, the Comprehensive Environmental Response Compensation and Liability Act, often referred to as the Superfund Law. It provided broad federal authority to respond directly to releases or threatened releases of hazardous substances that may endanger public health and the environment. So I'm going to kind of give you a really quick overview of the elements of CERCLA. One of the aspects of it is that there is joint and several liability, meaning that any party that contributed to the contamination of a site can be, liable for the cost to clean up the contamination. Even if you're somebody who had, say, waste shipped to that site, if they can't find another responsible party, you may end up liable for more than your share of the cost. This slide gives you a quick summary pictorial graph of the CERCLA cleanups process. There are approximately 8 steps in the process, starting with the preliminary assessment site investigation step or site assessment, in which typically EPA, or it could be DTSC, would review historical information about activities that happened at the site that might have released hazardous waste or hazardous substances. There's a site visit to evaluate potential releases and to determine whether the site poses a threat to people and the environment, including whether there are immediate hazards that need to be taken care of immediately. The next step is the remedial investigation feasibility study step, or site characterization, where the agency, typically EPA, evaluates the nature and extent of contamination at the site, the potential threats to human health and the environment, and performance and cost of the various options that might be available for treating the contaminated site. So after this site characterization step comes the decision step. There's a record of decision that explains which cleanup alternatives have been selected, and a preferred remedy is recommended in the proposed plan, which is submitted for public comment. After public comment, there's a final record of decision, and that then takes us to the next step, which is the remedial design and remedial action step. During that step, a detailed cleanup plan is developed and implemented. Remedial design includes putting together engineering drawings and specifications for a site cleanup, following that actually constructing and implementing the cleanup. Then once the cleanup has been completed, the post-remedial action activities include finishing any construction. There might be ongoing pump and treat of contaminated water, say, for example. Other post-remedial work could include routine monitoring of the soil or the water to see if there's maybe a contaminated plume that's continuing to move in the soil or water. There might be long-term site restrictions. There might be fencing around the site or restrictions on what types of activities can happen at the site. Once cleanup goals are achieved and sites are fully protective of human health and the environment, then they are removed from the national priorities list of contaminated sites. So my department, DTSC, cleans up or oversees approximately 220 hazardous substance release sites at any given time and completes about 125 cleanups more or less each year. There are another 250 sites on our EnviroStore database of properties that may be contaminated that aren't under active cleanup. After that very quick snapshot of CERCLA, the Superfund Law, I'm going to transition to our next topic, which is hazardous waste statutes under the Federal Resource Conservation and Recovery Act, which was enacted in 1976 and amended in 1984, and California's Hazardous Waste Control Law. The regulations for California's Hazardous Waste Control Law mirror the federal RCRA regulations very closely, almost word for word. Both the RCRA framework and California's Hazardous Waste Control Law have a concept called Cradle-to-Grave tracking and responsibility. There are a number of entities that are identified in the RCRA and California Hazardous Waste frameworks. The 4 kind of general categories are generators, people who produce hazardous waste, that's the generator, people who transport hazardous waste, and people who treat, store, or dispose of hazardous waste. So the way people enter the hazardous waste regulatory system is by producing a waste. Producing a waste can be hard to define point in time when that happens, but it's when the person decides or determines that the material they have is something they no longer want. It might have become used up or contaminated. It may be old and not used. It could be just something that's inherently not valuable. Whatever moment the person generates a waste, when they decide they don't want it, that's when it becomes a waste. And producing a waste triggers some requirements. The person who generates the waste needs to determine whether or not the waste is a hazardous waste or whether it's simply solid waste, or California calls it waste. There are two broad categories of hazardous waste that I'll talk about in subsequent slides: listed hazardous wastes and characteristic hazardous wastes. So we talked about the person who makes that determination, the person who is the person who generates a waste. Once you've done made the decision that you don't want something, you have to do the determination and then manage the waste accordingly. If the person makes a determination that they have a hazardous waste, they need to have already notified either California DTSC, the department I work for, or federal EPA, and obtain an identification number. Once the hazardous waste has been generated, there are limits on how long it can be kept at the site of generation before it has to be sent on to a destination facility. When it is shipped off, the generator has to use a document called a hazardous waste manifest. There are now online manifests, but the concept is the same. It is a paper trail or an electronic trail from the generator to whatever the final destination is. So in the paper format, copies of the manifest are sent back to the generator when the waste reaches the destination that he or she has sent it to, and that still is the same concept for the electronic manifest. The generator cannot just send hazardous waste anywhere. They have to send it to a facility that is authorized to receive it, which generally means that facility needs to have obtained a hazardous waste facility permit. Obtaining a hazardous waste facility permit is a big deal. It's costly. It involves site plans, engineering drawings, certification of tanks, inspections, a public notice and comment period. So it is not a small task to become authorized as a destination facility, generally speaking. So kind of digging into this waste determination bit a little bit more, there's a series of questions that the generator asks him or herself to do this determination. One, do I have a waste? Is this a discarded material that I do not want? And if it's a waste, is it carved out and excluded from regulation as hazardous waste? There are some exclusions in the statute that certain things are just by definition not waste or not hazardous waste. And the second part of number two is it exempted? So there are things that are hazardous waste but exempted from the rules for managing hazardous waste if they're handled in certain ways. And we'll talk a little bit more about that in later slides. So assuming you have a waste that is not excluded or exempted, the next question the generator needs to ask is, do I have a waste that meets the description of any of 5 lists of hazardous waste in California's regulations? We've incorporated all of the lists of hazardous waste that are in the federal RCRA regs in California, so you're covered if you're checking the California regulations. And if the answer to that question is no, the next question is, does the waste I have exhibit any of the 4 characteristics of a hazardous waste? So I'm going to talk a little bit, I'm going to kind of unpack this a little bit more on subsequent slides as far as what the lists are about and what the characteristics are. There are 4 lists of hazardous waste in the federal RCRA regulations. I have the section numbers at the top of the slide here, and they're referred to as the F, P, K, and U lists. The F lists are waste generated from common manufacturing or industrial processes. So they're not specific to a very particular process or industry. An example of an F-listed waste is the second one on the list, F002, which is spent halogenated solvents. So, for example, used methylene chloride that has become kind of dirty or contaminated and can no longer be used would be F002 hazardous waste. The second RCRA list is the P list. These are acute hazardous wastes, meaning that they're acutely hazardous, meaning they cause harm really almost immediately upon exposure from discarded commercial chemical products. An example is P001 waste, which is warfarin. Warfarin is a pesticide. It's used as a rat poison. So spent or unwanted rat poison is P001 waste. The third list is the K list. These are very specific wastes generated from specific industrial processes. They tend to have a very precise definition. Spent pickle liquor from chrome plating, things like that. They're very arcane. If you don't have that, if you're not working in that industry, you're pretty confident probably that you're not generating a K-listed waste. The fourth list are the U listed wastes. These are discarded commercial chemical products. So these are actually pure chemicals that are, for one reason or another, discarded. They're off specification, they're expired, they're old, they're surplus. For whatever reason, they're unwanted. For example, U001 is acetaldehyde, the chemical acetaldehyde. So in addition to the 4 federal lists of hazardous waste, which are also incorporated into California's regulations, we also have our own list of mercury-containing hazardous wastes in California, which is called the M list. And there are 4 M-listed wastes. Each of those is a specific kind of mercury-containing product. For example, fluorescent lighting, when it's discarded, is an M-listed waste. Even though the amount of mercury in discarded fluorescent light might not be very high, the concentration doesn't matter. If it meets the listing description, it's a hazardous waste by definition in California. So those are the 4 lists, a federal list and the 1 California list. So let's move on to the hazardous waste characteristics. So a characteristic hazardous waste exhibits one of 4 characteristics that are shown on this graphic here. There are ignitable wastes, reactive waste, corrosive waste, and toxic waste. And toxic, we have to sort of unravel that one even further, and we'll do let's start with the ignitability characteristic though. So all of these things are defined, most of them, with one exception, are defined pretty precisely. So ignitability means it's a liquid waste with a flash point below 140 degrees Fahrenheit or 60 degrees Celsius. Or if it's not a liquid and is capable under standard temperature and pressure of causing a fire through friction and absorption of moisture, etc. You can read the definition. Or if it's an ignitable compressed gas, or if it's an oxidizer. So a discarded material that meets any of these criteria exhibits this characteristic, ignitability, so therefore it is a hazardous waste under the state and federal characteristic of ignitability. Second characteristic of a hazardous waste is corrosivity. There are 2 parts to the corrosivity characteristic. There's a pH part, which is if you measured the pH of a liquid waste and it's below or equal to 2 or above or equal to 12.5, meaning it's either very acidic or very alkaline, it is a corrosive hazardous waste. California has a second element to the pH part of the corrosivity characteristic. If you have a non-aqueous waste, say some kind of a solid, and if you mix it with an equal part of water and measure the pH, then if it's equal to or below 2 or equal to or above 12.5, it's also considered a corrosive hazardous waste, so it would exhibit that characteristic. There's also a second element to the corrosivity characteristic, which has to do with how fast the waste corrodes steel. So a liquid waste that corrodes steel at a rate of 6.35 millimeters per year or higher is a corrosive waste. So it might take you a while to determine that, but maybe you could do it for a month and kind of extrapolate from there. Non-liquid waste that mixed with an equal part of water, same deal. If it corrodes steel at a rate of greater than 6.35 millimeters a year, it's also corrosive and exhibits this characteristic. So just to kind of reiterate, if the discarded material meets any of the characteristics, then it's a hazardous waste. It might meet more than one, but it only takes one to change the status from waste or solid waste to hazardous waste. The reactivity characteristic is a narrative definition. So the other ones, as I mentioned, have some fairly precise, specific criteria for determining whether or not your discarded material meets the characteristic. In this case, it's narrative. It just says wastes that readily explode, undergo violent reactions. So there may not be a test method. The generator just needs to use his or her knowledge. A lot of times this could be determined retroactively, that if there were an explosion or a violent reaction due to maybe mismanagement of some kind of a waste, then an enforcement agency might sort of determine that the fact that it reacted or exploded meant that it was a reactive hazardous waste. So somebody could be maybe written up for a violation of the hazardous waste regulations for mismanaging that waste. So this brings us to the final of the four characteristics that a hazardous waste can have, the toxicity characteristic. And this is the most sort of complicated of the four hazardous waste characteristics. There are 8 parts to the toxicity characteristic in California's regulations. We have the federal TCLP, which is a testing method that they established in federal regulations for taking a sample of waste and mixing it with a solution of acetic acid, shaking it for a period of time, filtering out the liquid, and then analyzing the liquid. And if any of the hazardous chemicals that are identified in the regulation is present above a threshold, then the waste exhibits toxicity. The rationale behind the TCLP is that landfills have liquid percolating through them, which is called leachate. It's from, wet garbage and things like that. This liquid is somewhat acidic, and it can dissolve hazardous constituents that might be present in landfill from other discarded items and carry it out into the leachate. So the leachate has to be disposed of in some way, and so the rationale is that if the artificial leachate in the lab is able to extract chemicals from the waste above some threshold, then that could happen for real in the actual landfill. So that's the general rationale for the TCLP. In addition to TCLP, we have additional elements in California only. This slide summarizes the 7 elements of the toxicity characteristic that we have in California that aren't part of the federal RCRA toxicity characteristic. So the first one is the toxicity threshold, total threshold limit concentration. It's this one, unlike the TCLP that I just talked about, is an analysis of a sample of the actual waste, not of a filtered liquid that was percolating through the waste. If you grind up and analyze the waste in a laboratory and determine that any of a list of about 20 chemicals is above the threshold that's specified in the regulations, that is enough to make the waste exhibit the toxicity characteristics, so therefore it's a hazardous waste in California. The next one is the soluble threshold limit concentration. That is another simulated landfill leaching method. It's slightly different from the federal method, but the concept is the same. If you mix the waste with an acidic solution, shake it, filter out the liquid, and analyze the chemicals present in the liquid, if any of the listed chemicals is above the threshold, the waste exhibits the toxicity characteristic based on the STLC. The next few elements of the toxicity characteristic in California are based on animal testing. And the first one, acute oral LD50, is the amount of waste that it takes to kill half of a group of experimental animals. So something that takes 2,500 milligrams or less per kilogram body weight of whatever the animal is, maybe it's a mouse, to kill half the mice treated, that waste would exhibit toxicity based on the oral LD50. The dermal LD50, same concept. The number is different, but it's applied to the skin of the test animal rather than ingested. Inhalation, same concept. It's present as a gas, and if the concentration is below 10,000 ppm in air that it takes to kill half the experimental animals, then the waste exhibits toxicity. There's also an aquatic toxicity element of the toxicity characteristic, the acute aquatic 96-hour LC50, which is a measure of how many of a group of fish die. And if it takes less than 500 milligrams per liter of soft water to kill half the fish, then again, the waste exhibits the toxicity characteristic. And finally, there is an element that says if the waste contains a listed carcinogen at 0.001% or higher in concentration, again, the waste is a hazardous waste. So the main takeaway from this is there are a lot of elements to the hazardous waste characteristic of toxicity in California. Generators need to either do testing to determine if their waste meets any of these, or they can use their knowledge of the waste. If they know that, for example, the waste is water, it's distilled water, say they know it's not likely to exhibit any of these, and they can just use that knowledge without actually having to test it in the laboratory or using animals. Now that we've dug into the definition of a hazardous waste in probably more detail than you're actually interested in, I'm going to transition to just sort of giving you a quick overview of what the ramifications are. Like, so suppose you determine you do have a hazardous waste, either because it's on one of those 5 lists or exhibits one of those 4 characteristics. What happens then? Well, as I mentioned earlier, hazardous waste generators, once they've done the determination, have to manage the waste according to different rules from regular garbage or solid waste. And they have to use certain types of companies to transport the waste that have to comply with certain requirements that are more stringent and additional to what a regular trucker or hauler would have to follow. So the general gist of the hazardous waste transporter requirements is that the transporter has to follow the Department of Transportation rules that apply to transporting hazardous materials. In addition to that, they need to use the hazardous waste manifest that I mentioned earlier, and a copy, the transporter has to return a copy of the manifest to the hazardous waste generator, the person who hired them to take the waste to the destination, so that the generator has a record of where the waste went. The hazardous waste transporter also needs to get an identification number from federal EPA or from Department of Toxics. This is just to keep track of who the transporter was. So as I mentioned earlier, the generator has an ID number, the transporter has an ID number, and the destination facility has an ID number. So there's a trail, a paper trail or an electronic trail leading from cradle to grave for the waste. In California, we have an additional requirement. The transporter of a hazardous waste actually has to obtain a special registration to be a hazardous waste transporter above and beyond the other requirements. So once the waste has reached the destination facility, there's another set of requirements, and this is the most sort of stringent and comprehensive requirements, which is the treatment, storage, and disposal facility requirements. People operating a treatment, storage, or disposal facility, or TSDF, are the most heavily regulated in the chain of people handling hazardous waste. As I mentioned earlier, they need to obtain a permit and operate according to its conditions. Typically, the permit is not just filling out a form. It's their book length, multiple book length documents that include things like site maps, contingency plans, chemical inventories, things like that. The permitted treatment, storage, and disposal facility also needs liability insurance in case their actions or activities cause any injury or property damage. They have to also have a plan for closure, which really means when they're done, when the business is no longer going to operate, how are you going to decontaminate and remove all of the hazardous waste that may have been there? In conjunction with the closure plan, they also need to estimate how much it would cost to implement that plan. So the reason for the closure cost estimate is they need to actually have money available, either through an insurance policy, a certificate of deposit, just money in the bank, something that will cover the costs of closure if the company were to disappear or go out of business. So that the rationale is to avoid some of the scenarios that we talked about earlier with contaminated sites with no responsible party available to fund the cleanup, because then the cost falls to us, the public, the taxpayers. So the quick overview I've given you of the requirements for generators, transporters, and TSDFs is the general rule for hazardous waste. But I mentioned earlier that there are exceptions to that. There are exemptions and exclusions from managing hazardous waste under the system that we just talked about. So one set of exclusions has to do with recycling. Hazardous waste that's recycled in certain ways is excluded either from the definition of hazardous waste or from the definition of waste altogether. For example, if you had some solvent that was used in a semiconductor manufacturing facility somewhere that required very pure solvent because the impurities would cause problems with the performance of the semiconductor, once the solvent has become contaminated so that it can't be used by the semiconductor company anymore, it may be perfectly good for the auto repair facility down the street. Without any further processing or reclamation, they could just take that solvent and it's still perfectly good for cleaning, say, car parts. So that would be a type of recycling that doesn't require reclamation, and it's completely excluded from being a waste at all. There are also a number of exemptions from regulation for hazardous waste managed in certain ways. The ins and outs and details of all these exclusions and exemptions is way too complicated to get into, but just note that it's a very complicated area of the law, and it's really designed to make sure that people are using the exemptions and exclusions appropriately. They were created to promote or encourage people to do things that were sort of better than sending things to a landfill or a special hazardous waste landfill. And we want to make sure that people are actually doing what was intended with the hazardous waste. I've touched on some of the differences between the hazardous waste regulatory system under the Federal Resource Conservation and Recovery Act and California's Hazardous Waste Control Law. This slide just kind of gives you a nutshell summary of some of those differences. So as we talked about earlier, the definitions of a couple of the characteristics of a hazardous waste in California, the toxicity characteristic and corrosivity characteristic, have additional elements to them in California that aren't part of the federal framework. In addition, California has some exemptions from regulation that don't exist under the federal RCRA hazardous waste regulations. We also don't have some of the exemptions that RCRA does have. For example, under the Resource Conservation and Recovery Act, waste that is generated by a small business, they use a term of art that used to be conditionally exempt small quantity generator. There's another name for it now, but basically small businesses that produce waste that would otherwise be hazardous, it's exempt from regulation as hazardous waste under federal regulations, but we don't recognize that exemption in California. Also, under federal hazardous waste regulations, waste generated by a household is just categorically excluded from being defined as a hazardous waste. Even if you were throwing away asbestos or lead or whatever it might be, if you're generating it as part of maintaining a household, it's carved out under the RCRA regulations, but we don't recognize that exclusion in California. We do have exemptions for waste generated by households, but we do not exempt it from being defined as a hazardous waste. So that's a whirlwind tour of the Resource Conservation and Recovery Act. Let's move on to the next topic, and the final topic is the Toxic Substances Control Act, or TSCA. Toxic Substances Control Act, or TSCA, is federal law regulating chemical safety in the United States. It was first adopted in 1976 and remained pretty much unchanged for 40 years until it was finally amended in the last couple of years, 2016 or so. And I will talk about those changes. So let's first talk about TSCA as it was originally adopted in 1976. All of the 62,000 or so chemicals that were already in use in 1976 were presumed to be safe, and so they were grandfathered in, so they weren't subject to the provisions of the law. The Toxic Substances Control Law, and keep in mind this is the main chemical safety law for the United States, did not require EPA to mandate that people using chemicals assess their safety. EPA actually had to find that there was an unreasonable risk before they could impose any restrictions on the use of a chemical. And they had to do a cost-benefit analysis. So even if there was an unreasonable risk, they still had to weigh whether mitigating or reducing that risk was worth it in terms of trade-offs for cost. So even if there is an unreasonable risk, EPA had to impose the least burdensome restriction that it could identify to address whatever that risk might have been. After decades of failed attempts to reform or fix the Toxic Substances Control Act, finally in June of 2016, the TSCA reform law was enacted by Congress and signed by the President. It was called the Frank R. Lautenberg Chemical Safety for the 21st Century Act, and it changed a number of aspects of the existing law. One of the changes was that for the first time, EPA was required to evaluate the safety of existing chemicals in commerce, starting with the ones that were the most likely to cause risks. The constraint that they could only consider the least burdensome way of addressing a exposure risk was removed, and the law required that EPA publish a list of its first 10 chemicals and start evaluating their risk within 6 months of adoption of the law. Under the 1976 version of TSCA, manufacturers were required to submit a pre-manufacture notice to EPA for chemicals, but the law didn't specify any requirements for what types of health and safety data needed to be included in that notice. Under that law, EPA had 90 days to review the pre-manufacture notice. If they didn't take action within that time, the company was given a green light and could start producing the chemical. So there was sort of a presumption of safety unless EPA took action. Under the amended TSCA, the Lautenberg Chemical Safety for the 21st Century Act, EPA is required to make an affirmative finding that unreasonable risk is unlikely before the chemical can go on the market. Here's some other kind of notable aspects of the TSCA reform Lautenberg law. Under the revised TSCA, a state cannot impose restrictions on a chemical relating to hazards, exposures, risks, and uses that are covered by an EPA risk assessment under TSCA. The states can initiate restrictions unless and until EPA has named the chemical as a high priority chemical and specifies what the scope of its planned risk assessment or risk evaluation will be. This actually could come into play with the Safer Consumer Products program that I work in, because some of the chemicals we are looking at are either under evaluation by EPA or might be. So if you want to learn more about the Safer Consumer Products regulatory framework, I have a separate lecture that should be posted by Mr. Dudman on your class site. However, I mentioned there's this preemption against states duplicating what is being done by EPA under TSCA. This preemption doesn't apply to information collection and reporting. For example, it doesn't stop California from requiring Proposition 65 labels for chemicals that are determined to cause cancer or reproductive harm. So that is my whirlwind tour of the Superfund Law, the Hazardous Waste Control Law, and TSCA, as well as some background on why we have these laws. If you have any questions about anything I've talked about, I've got my contact information on this slide. Feel free to send me an email or give me a call. If you're interested in the work of the Department of Toxic Substances Control, I encourage you to look at our website, dtsc.ca.gov, and the same URL with SCP after the slash will take you to the Safer Consumer Products webpage where you can learn about the program that I work in. Thanks for listening, and have a great rest of your semester.